let's crack on. So, this is a review class of the review classes. Both the Monday and the Tuesday were reviews of the Unit 1 and 2 and Unit 3, 4 respectively, and now we're doing a review of the reviews. So as far as where to start, I do think doing the stuff out of the Unit 3, 4 book will still be most beneficial overall, because yes, there's calculus involved in these, which Unit 1 and 2 doesn't need, but a decent number of the questions aren't necessarily going to need it. Yeah, you got a question?
Yeah, can we look at one question from the test tags that you have in the
Yep.
calculus section? Yeah, I was doing one of them and I was having a little hard time with one of the questions.
Sure. Which one was it?
Test tag 1, question 7, I think.
SAC 1,
Tech
question
3.
7, tech 3. Okay.
Yeah, I think that was it.
Does this look familiar?
Wait, yeah.
Yeah. Okay. I'm assuming the diff was fine for you, but let's just get that going because I'm assuming we'll need it. Okay, diff of this is going to be chain rule. Why? Because we got a composite function, right? It's not just natural log of x there. So let's get our chain rule going. First of all, u is x squared plus 4, u dash 2x, y of u, natural log u, y dash u, 1 over u. Chain rule, multiply them together, 2x over u, which is x squared plus 4. Okay, cool. From there, hence find the value of b if the average value of that function f of x over that domain is equal to that. That keyword there, average value, did you recognize it as a specific thing to do?
Oh, sorry, I didn't get you. Can you repeat that?
Yeah, so there's the keyword there, average value. Do you recognize that as a hint for what to do next?
Average value.
It cut out a little bit there, sorry, could you repeat that?
Wait, the average value, I guess
Mhm.
we have to find the sum of it. And wait, no, wait, I can't remember.
That's fine. So that's probably why you were stumped here. The average value is somewhere in the applications of integration. It's a genuine, it's a flat out equation to use. So this is your average value equation. As long as you know the domain, you just divide by the length of the domain and you'll find the integral of that function over that domain. So when we're talking about average value being equal to this, it means that integral is equal to that. So in other words, we had 1 over, I guess it's just b because it's 0 to b. That's the length of our domain. Then it was 0 to b for our terminals and the function. So I'll just use f of x just to be a bit shorter with it. And that is equal to the natural log of the bth root of 2. Okay, equal to the natural log b root 2. That's how we're supposed to start this one, with the actual average value formula itself. Is that fair enough so far?
Yep.
Okay. Now that you know where this is at, any ideas on what we're going to do to start solving for b?
Um, do we just solve it like a normal? Sorry, do we just solve it like a normal integral?
We can try, however, one of the things we're going to notice is f of x is a division of two functions, and we don't really have like a quotient rule equivalent for integrals.
Yeah.
So if I were to write this out properly, 1 over b integral 0 to b x over x squared plus 4 dx is equal to the natural log of, let's do this instead, 2 to the power of 1 over b. We use the index version of the root instead. So just integrating this, tough. The hint is there's a reason part A exists here.
Oh, do we have, wait, sorry, I just, Friday afternoon, I just,
Yeah, that's
my
right.
brain's not working.
I get you.
So, do we have to, I, integration by identification or?
Yeah, that's right. We're doing the integration by recognition thing, because what you've noticed is if we have a look back, we did our diff of that function is equal to 2x over x squared plus 4. So basically our, I don't necessarily want to say f dash x, I'll just say, I don't know, h dash, because f is a slightly different function. F they've defined as just the x over x squared plus 4. So basically we figured out that the diff of our part A function is that. So in other words, if we integrate both sides of that equation, we should get right back to the natural log.
Yeah, yep.
Yeah.
Okay, so,
We have d
hmm,
on dx, and that's applied to the natural log x squared plus 4 is equal to 2x over x squared plus 4. And all we're doing is slapping that integral on both sides.
okay,
That'll cancel out. Natural log x squared plus 4 is equal to the integral of 2x over x squared plus 4. Just turn up the brightness on this real quick so it's a bit clearer to see. Cool. So that's pretty nice because it gives us an integral relationship that we couldn't otherwise find, but it's still a little bit different, right? Like these two things are not exactly they're not identical, right?
yeah,
What are we going to do about it?
okay. Hmm. The left-hand side is a natural log, right?
Yeah, natural log.
Okay. Um, so I guess integrating that would be something similar to a natural log. Wait,
Yeah, so this equation here just says the integral of this is that. So by doing this
yep.
whole integration by recognition process, we're bypassing the need to actually do an integration.
Oh, yeah, okay.
The challenge that we have is, yes, we got an integral relationship, but it's not the same. Like this is just x over x squared plus 4. This is 2x over x squared plus 4. So if I want to make use of this, I need to rearrange something in here to make it identical.
Oh, so can we just take out the 2?
That's it. Yeah, you take the 2 out, just works the same way as diff, and then obviously from that point on you're just dividing by 2 to get the integral on its own. Half natural log x squared plus 4 is equal to the integral of x over x squared plus 4. Or in other words, this is our capital F of x. Now that we know our capital F of x, that's going to help us do this actual definite integral. We have the first part of it. All we're going to do is evaluate now capital F of b minus capital F of 0. Now, I would do a little halfway step here, which is also to get this whole definite integral on its own. So in other words, just putting b over here. So that's going to get us,
Okay.
yeah, because when I'm just evaluating the definite integral, you can just evaluate it directly and just chuck it back in here and replace, but you might forget there's a 1 over b there. So a nice little halfway step would be to also get that integral on its own as well. Integral 0 to b x over x squared plus 4 is equal to, so that's just going to be b times the natural log of 2 to the 1 over b, which, for those who've done logarithms, something in there can be simplified even further.
The power
Yeah, that's
power
right.
inside the logarithm, we can take it out.
That's it. Using the power law, you can take that out as a coefficient. 1 over b times b, well, they just cancel out. So this integral we know has to equal natural log of 2. Or in other words, capital F of b minus capital F of 0 equals natural log of 2. There's the b,
Good.
so we're still going to have b in this equation. We haven't fully gotten rid of it. And then, yeah, the rest of this is just the arithmetic side of things. Let's suss it out. Actually, maybe I'll pull up the answer sheet. Let me see if that's got it fully written out at that point. Save me from having to do all the arithmetic in front of you if it's got the work steps already. B. Okay, it's a bit messy. Yeah, a bit messy. Let's just do this. Okay, cool. So capital F of B, we're going to now have, it's this function here. So half natural log b squared plus 4. Yeah, that's all it is. Minus capital F of 0. So minus half natural log of 4. The 0 squared disappears. And that is equal to our natural log of 2. From here, they both have halves in there, so you might just get rid of all these coefficients and multiply both sides by 2. Natural log b squared plus 4 minus natural log 4 is equal to 2 natural log 2, which I'll just do a little double step there and also put that in the power as well. So instead of having that coefficient of 2 at the front, we'll use the same law as before to put that in the power. Doing that because I noticed that these will now be identical. So when I go ahead and try to do some more rearranging, I can condense them down a bit easier. Which I'll do next, right? Plus natural log 4, 1 natural log 4, 2 natural log 4s. Natural log b squared plus 4 equals, again, 2 natural log 4, which we can then change to natural log 16, 4 squared, 16.
Yep.
And yeah, now we're just equating the insides. If you have the natural log of one number equaling the natural log of another number, well, all we're doing now is looking at the inside of those brackets.
So b squared plus 4 equals 16. 54 to the other side, that's 12. B equals to the square root of 12.
Yeah,
No,
we'll start with plus
minus,
minus just in case.
Yeah.
And then you just sort of rationalize it. What is it? Simplify the third. So 4, 3.
2 to 3.
Yeah. Last check. Is there a thing where b has to be positive or negative? Can we knock one of those out?
Yeah. B is positive.
B is positive? Why?
Because it's 0 less than or equal to x, less than or equal to b.
Yeah,
so
that's
b
right.
must be greater than 0.
That's exactly right. From the question itself, the interval is from 0 to b, so b has to be greater than 0. Yeah, that's pretty much it there. So it sounds like when you were doing your studies, the only thing that was tough was you didn't understand average value meant an equation specifically.
Yep.
Because then, yeah, from there, once you have your average value equation, then it also becomes an integration by recognition thing. So there's actually 2 applications back to back. I guess it makes a decent amount of sense why it's even 3 marks is, yeah, 4 marks for the whole thing, I suppose.
All right, thanks.
Yeah, no worries. So yeah, a nice little lesson there in also looking back at your previous answers in these exam or SAC conditions, because, oh, yeah, time.
Oh no, I was just gonna say like these multi-part questions like pretty common like for A and B and stuff. I feel like it's really annoying because I've had tests where it's like where it said hence, but then if you haven't figured out the first part, then you can't do the second part, even though you would know how to do the second part. So
Yeah, it's
that's happened to me a couple times.
it does suck like that, absolutely. Yeah. And they do in the actual exam, they do have, I've seen it in the exam reports, they do say, hey, there is marks awarded for consequential, but it's very limited. One is the thing you're pointing out, which is I have no idea where to even start because I haven't done the part A yet. But even in the questions where you do have at least a reasonable guess as to where you would go next, your marks are limited to process. So, like, if you know, for instance, just based on the wording of this, hence find the average value. I mean, it's kind of hard to assume that this is going to look like that. Yeah, this one will be very tough to get any consequential marks out of.
Yeah.
You're right.
Actually, I was wondering as well, like, because I've heard from methods like there's a lot of marks allocated to working out. Like, even if you don't get the right answer, like, how does that normally work?
Well, yeah, it's only ever one mark for answer. Every other mark that you see is for working out.
Okay, yeah,
That's the gist of it there. Yeah.
yeah. So it's normally like 1 mark for your answer, and then the rest for if you've done the right process, basically.
Yeah. Well, a logical process to get you there.
Yeah,
A decent number of questions have multiple ways of getting there, especially that's why they'll often say hence or otherwise. This one didn't have it specifically, but this is also not exactly VCAR. This was from a different exam provider. Yeah.
yeah,
So the wording might not be as tight, but a lot of the VCAR ones will say hence or otherwise because it does imply that there are other ways of doing it, not necessarily leaning on your previous answers.
yeah. That makes sense.
But
Thanks.
yeah, in summary, making use of the previous answers in your sequence A, B, especially when they go into like I and double I and triple I's, all those little indents tell you that anything within that specific indent is likely going to be relevant in your next section of in your next set of questions. Cool. Did anyone else have any specific things that came up in their studies? More than happy to pull them up if I got a copy of them. Have a think about that.
I was wondering, have
Oh,
we
yeah.
covered Newton's method yet?
We have, yeah.
Remember?
But I can go over something specific if you wanted to.
I think there was. Oh, I think it was. I was a bit confused about the situations where Newton's doesn't work. Like, I think it was like the
Yeah,
oscillating sequence and the terminating sequence.
yeah, exactly right. So let's just make sure we're all on the same page as to what Newton's method actually is, firstly, because that'll allow us to better understand why it doesn't necessarily work every single time.
Yeah. Can we
So
like also just review it just pretty quickly as well?
yeah,
If we have
yeah, I'm
time.
going to basically review from the
Yeah.
start.
Cool.
So what Newton's method is a algorithmic approach to solving the x-intercepts of a function. So essentially, not all functions can be solved via algebra. This is the reason why things like this exist. Your CAS does this sort of thing when it approximates functions and getting for your x values or whatever you wanted to force it to solve for. It might not use Newton's method specifically, but it uses some sort of algorithm to hone in on a value until you get whatever precision you're looking for. How Newton's method works is basically, as long as you're roughly familiar with where the x-intercept is going to be, like if you were to plot this quadratic, you could dot out the rough, it's a relationship, right? You can dot out where the x and y pairs are, and you can get a rough estimate as to where your x-intercept is. So long as you know where that is, if you take a tangent at somewhere in the ballpark of where that is, what you'll find is that the tangent that you've taken, its x-intercept will be closer to the one that you want. So for instance, we initially guessed x equals 4. That gave us the blue line to get 9/4. What we'll notice is that that is closer to the red x-intercept that we want. If we then repeat the process, take my tangent line here now, getting the yellow line, we'll notice it gets closer again. Rinse, repeat, take tangent lines until you are sufficiently close to your x-intercept. That's what Newton's method actually is. There's a formula for it. All we're doing is rearranging the y equals mx plus c for the linear that you're creating. All right, we're just rearranging that, and we're using derivative notation because we're using derivatives to get our gradient. That's all that is. So in other words, you can use this repeatedly as long as you know f of x, its derivative, and the subscripts there are basically telling you what x value you're on in the sequence. Xn is the current value, and xn plus 1 is the next that you will get. So in other words, if you started with x equals 4, xn would be 4, and xn plus 1 would eventually be 9/4.
Do we get will we get the Newton method formula on our formula sheet?
Yep, it is. Oh, this is an old formula. Where is it? There we go. Yeah, you get it there.
Yep. Cool.
Okay, so now that we're familiar with what Newton's method actually is and how it works, now we can start thinking of ways that it might break. First is the term oscillating sequence. What's happening in the oscillating sequence is that the next x-intercept that you use, if you take a tangent line at that spot, that tangent gets you back to the previous x-intercept. So it's blurred out. It's drawn in white for some reason, but there is a tangent line there. You can kind of see it cutting through a little bit. Basically, we have this black tangent line. It intersects here. That tells us that our next tangent should be directly vertical from that at that x value. The tangent occurs. Next x-intercept. Oh, it's the one that we had previously. This sequence will repeat forever, never actually getting closer to 0. We see this in a basic cubic here. Odd functions like this are likely to do that sort of thing. But yeah, this is just one way that Newton's method can break. The other thing that can break it is the terminating sequence. Terminating sequence is what happens when your x value that you're guessing ends up being a stationary point. The reason why that's bad is because if you take a tangent at a stationary point, it's perfectly flat. It never touches the x-axis anymore. So if it never touches the x-axis anymore, you don't actually have a next guess, right? It terminates. It ends early. Those are your two fail conditions there to watch out for. The one that I've seen show up in the exam is a terminating sequence. That was exactly this, where they got you to find the stationary points of a function and then said, hey, what if I did my Newton's method there? What's wrong with that?
What makes something a terminating sequence again? Is it just having stationary points?
If you choose a stationary point, or if you eventually get to a stationary point where you're going to take your next tangent, I'll demonstrate it with a graph. So we have our function, whatever it is, and I'm doing my tangent lines. I don't know, let's say I do a tangent line here, and it ends up looking kind of like that. Then my next tangent line now has to be there, because that's where the x-intercept was. And I'm going to try my best to draw a horizontal line. This does not touch the x-axis anymore. I have no other spot to do a next tangent line at. So basically, if you ever get to that stage where you do have your next guess on the stationary point, you can't continue. Cool. Anything else from here you wanted to clarify further? Anyone else too. If anyone else has anything they've come up with in their studies, we can have a look at that as well. Feel free to drop that in the chat at any point. Even take some time to look through your notes or whatever, and we can address it a bit later if you want. Either way, if there's nothing else, then probably a decent place to start would be this question 7 here. Tech active, external response, because that tends to be the hardest type of stuff. Question 7, AI. I'll let you guys have a read of that. I'll just start putting some stuff in the CAS to get ahead of the curve. Oh, sorry, this is 7A here for the Unit 3-4, if you've got your own textbook.
Wait, sorry, what part of it was it again?
This is 7A up here, Unit 3-4, chapter review 12.
12,
if
okay.
you got that one.
Oh, sorry, I was on 12B, that's why.
Yeah, the multis. And for those who don't have either of the books, I've just dropped both of them in the chat there, Unit 1 and 2 and Unit 3-4. But okay, cool. So our population given by a function made up of exponentials there, more specifically decaying exponentials because they got the negative coefficient in the top. And it's a population equation. Population specifically that has the virus, the proportion of the population. So in other words, if it came out to be like 0.1, then that would mean 10% of the population has that virus at that given time value. So AI asking us to find the proportion of the population which has had the virus up to 10 days after its introduction. We want proportion and we're given time. Proportion is our y value, it's the proportion of the population, and it's a function of time. So time is like our x-axis stuff there. So this is just asking us to do p of 10 here. I'll just quickly check. Yeah, t is in time. T is in terms of days there. So 10 days after, t days after. We're using the keywording in there. Each 10. That's going to give us, well, actually quite similar to the guess I had. That'll be, what are we doing here? 4 decimal places, proportion of population. So 1155. Any questions on the interpretation of that? If not, feel free to move on to the next one. And with II, find the proportion that eventually catches the virus. This is there's a few ways to word this in similar style questions. Yes,
Yeah, I was curious about the wording for this one because when we say like eventually, it's not really like a time.
Yeah.
Like how do we just determine like what to calculate?
Exactly. Eventually is a time, but not like a t equals time, right? It's just like, what the hell does eventually mean? So they have different ways of wording this for exponentials, depending on what they've described the function as. Eventually just means, what's a nice easy way of explaining it? Eventually just means like assuming t equals infinity, like all the way out till end of time, what is the final resting steady state value of the function? That's what they mean by eventually here. Sometimes you get like exponentials that are related to like heating and cooling, and they'll say, what temperature does the room finalize at, or stuff like that. Any time value that is not necessarily a given value, this kind of wording is implying like t equals infinity here.
Yeah, so we'd find some kind of value like, after some time, the virus would stop spreading and we'd get like a stable value or a stable proportion of the population that's infected.
Mm-hmm. Yeah, that's right. Our goal is to figure out what do we stabilize at. You can do this a couple of ways. You can actually do it just by looking at this function and understanding your exponentials. Alternatively, we have a cat, so we can graph this, and we can just shoot the axes out as far as we want, and you'll soon see if you shoot it out far enough, you'll definitely converge on a value. You also have limits if you want to use limits, and you can do, I think you can do direct substitution actually as well. Any ideas on how we'll go about it? Or even what the answer might be? Okay, so assuming we know nothing about the functions, right, and pretending they're too tough to understand, graphing it is the easiest way to go about it. Oh, hang on. Yeah, I'll give this a read in a moment. Yeah, so graphing this will be the next best way of going about things. Simply just trying to evaluate what do we actually reach. You can use min, max, doesn't really matter which way you go about it, probably max. And just, do some boundary over here. All we're trying to do is estimate what roughly is out there. And what roughly is out there is the y value 0.2. Proportion we're going to reach up to 0.2. That's the graphical way of doing that. The other thing you can do, so long as you understand that we are trying to figure out what happens eventually, is you can just sub in infinity and get the 0.2 as well. The last way you can do it is understanding that exponentials, if they are decaying exponentials, t equals infinity. If you sub that into those t values, you now have an exponential that has an infinitely big negative index, so those terms just disappear. And what you'll see is left over is the 0.2 at the front there. Do we have any questions about how that one works?
So, I don't know if I'm just a bit confused, but with the 0.2, what's that number?
The 0.2 is the final population proportion.
Okay, yeah, okay, I see.
Yeah, we subbed in our t equals infinity, we got 0.2 for our population proportion there.
Cool. Oh yeah, because PT is given by that equation.
Yeah, that's right. Because yeah, that's our P of t equation. All good?
Yep.
Nice. Okay. Next up, and final for question 7. Let's see. Number of new cases on day t proportional to p dash. Find how long after the introduction the number of new cases per day is at a maximum. Number of new cases on day t is proportional to the derivative. Find how long after the introduction. Okay. I'm not entirely sure why that's relevant. Why that first part is relevant anyway. I guess it's maybe just reminding us. Number of new cases per day is at a maximum. So it's not like when is the population at its maximum. That's a bit different. It's the number of new cases on that given day. Yep.
So do we have to find the double derivative for this?
Yeah, we could, I think, because double derivative. What makes you think double derivative? Firstly.
So it's number of new cases per day.
Yep.
Yeah, I don't know how to explain it.
So what's probably going on in your head is you're thinking, okay, so we're looking for maximum gradient, not necessarily maximum y value, because gradient is the rate of change or the number of cases you're getting any given day. So
Yeah.
if you have your derivative and you want to find the maximum of the derivative, you now need to do the derivative of the derivative to get there. Yeah, double derivative will get you there. Double derivative equaling 0, I guess, in this case, because you're looking for the stationary points of the derivative. It does, even as I'm verbally describing it, get a bit confusing to probably think of it that way. So one of the things we can use is just our graphical approach, right? Yeah, Tahan?
Sorry, I don't know if it's already been said, but if you were doing the derivative, so you differentiate it first, and then get the max by double diff and equaling to 0, right?
Yeah, that's the idea. That's one thing you could do for it, assuming, of course, that the maximum is a turning point. So that might not be the case because these questions can break a little bit like that, which is why what I'm going to suggest, at least initially before you do that, is just graph the derivative and see, do we get what we expect? Or do we get anything reasonable from that? So let's see. What are these settings? That doesn't look too great. Did I do my derivative wrong? Well, it is a function. Okay. 1, let's go with negative 0.1. Okay. Still a little bit. Yeah. Okay, so it does look like it kind of curves up and then reaches some steady state of flat at the end. So yeah, an initial bump implying a turning point seems pretty appropriate here. So yeah, 93.1, set the derivative of the derivative equal to 0. ddx of now ix equals 0, comma, x. And that seems about right. We saw that was an initial bump very close. That'll be the time value. So the other thing that I was going to suggest there would be fmax for the derivative function, because fmax will, if you're ever in doubt as to whether or not your maximum is at a turning point, this one will find any maximum. And sure enough, they ended up being the same thing in this case. So as for how you give your answer here, they didn't say round, so we're going to give that 20 natural log 2 as our answer. Or 2 to the power of 20 in there if you really wanted to do that, rather than rounding. We all good for that one? Awesome. Okay, we're going to take a detour into 5e now. So 5e, what was that? .5e is on the piecewizers. Okay, so a quick review on the piecewizers. Was it around how to sketch the piecewizers that was the issue, or were you coming across other questions that were a bit challenging? How to sketch them? Yeah, okay. So how to sketch them pretty much boils down to doing each of the individual functions over their relevant domain, right? So you read your piecewise functions like a book, left to right and then down. So all these individual functions, if you look at them from left to right, are stuff that you should already know how to sketch for those. If it comes to, as you said there, find the range domain and all that sort of thing, that's where things will definitely get more trickier. So in 2 steps, essentially, step 1 is figure out, okay, do I know how to solve, or sketch rather, each of these functions individually over their respective domains? If that's okay for you, then we move on to the next thing, which is, okay, now let's put them all on the same axis. That's all we're basically asking here. So if we do like 5a here, for instance, let's have a look. 5a is made up of 2 linears and a quadratic. So as long as we're familiar enough with how to sketch linear and quadratic, we'll be happy. So let's have a look. First one for 5a there says we're sketching x plus 3 over the domain x is less than -3. So one way that you can do it is simply just start by sketching the graph as if there was no domain there. So graph of x plus 3, it's going to have a y int at 3, and that'll be an x int at -3. And then you can just sketch the whole thing there, and only after having sketched the thing, then restrict the domain. So this one said it was from less than x equals -3. So we're going to make sure that we cut off everything left there and leave an open circle specifically because it was non-inclusive. It's x less than -3. We all good so far? Next up would be the quadratic. So the quadratic x squared minus 9, we know that's just shifting the turning point down at -9. And if you solve for the x-intercept, you'll find out they'll become plus -3. So going to connect on there, and we're going to have another copy of it here. These are both going to be inclusive, so we're now going to make sure we redraw over that because they do end up sharing that point anyway, because it's inclusive on the -3, again, inclusive on the +3 there. When you have an inclusive immediately over an exclusive, you just default to the inclusive. That's going to get us the second part. The third part is another linear. It's x minus 3 this time. So it's going to have that y int of -3 and cut at x equals 3. So that would be like that. Again, we'll restrict our domain to be x greater than 3, as suggested by the 5a f of x. So we only want this last part, and we would be putting an open circle there if it didn't already have a closed circle there. This graph turned out to be fully continuous, right? All the joins of each part of the function actually joined up with each other. If they didn't, like let's say, I don't know, we found out that it started up here instead, then yeah, just you're allowed to have them be disjointed so long as they actually are disjointed. That comes up a decent amount, but not always. Fair enough on at least getting the graph going. Anything to clarify about that one? What should I do when the piecewise functions intersect? Sometimes the graph given is a bit small, hard to draw. Okay. If you're given an axis that's too small to work with, that just kind of sucks. I don't really know what else to, what other advice to give there. Like when you get these axes, are they like labeled out with the ticks, like they got grid boxes? Yeah, they had grid boxes. Okay, how do you get them all in the same axis then? Yeah, I mean, it could just be the case that your teacher maybe just didn't make it big enough to work with. I don't really know how to give any advice on how to fit them all in because when they have the grid, if anything, it's more strict on what it should look like because now your parts of the curve can't just sort of be free-handed like I'm doing. Now this one didn't necessarily have any key features that really needed, like turning points, for instance, that were on like out here or whatever. We didn't have any of that to worry about. But yeah, usually with the grid, it ends up being easier because you can just sort of dot it out and literally draw out, literally do the equations, right? So if you have these little grid lines, at x equals 1, you can just shove in x equals 1 into your function and see what grid line that should intersect with. Yeah.
Yeah, I was wondering, can I have a different scale for like the intervals for like 1, 2, 3, 4? Can I have a different scale for, say, the positive axis and a different scale for the negative axis?
Yeah. In fact, a lot of the times you should.
Yeah.
Because, yeah, if you have the same scale, well, we saw how it looked. Pretty much every time you put something on the CAS, you got to mess with one of the axes because one of them is busted. So yeah, you'll pretty much always need to make. Usually the Y needs a bigger range than the X does.
Oh no, I was wondering specifically like for positive Y, if I had a different scale to negative Y.
Oh, that.
Or is that not really allowed?
Nah, not that, unfortunately.
Okay.
Y-axis has to have the same scale. X-axis has to have the same scale. X and Y are independent of each other, but negative and positive Y are consistent with each other. Yeah, that one you have to maintain.
Yeah. No, sorry, I was asking because I've just had some graphs where it's just a bit weird, so.
Yeah. Was this like a... I guess it's all school provider stuff, yeah?
Yeah.
Yeah. Maybe send me a photo of some of the stuff you're talking about, and I'll see if I can. Maybe that I'm seeing it in person. It'll be a bit easier to give any more better advice regarding it. But yeah,
Okay.
it's initially my thoughts around that are going to be make sure your axes are consistent for Y, and just sort of I guess cope with what they've given you.
Yeah, and I assume that would be the case. So I was just wondering, like, yeah, if it's something that you can do or not.
Yeah, no, you have to keep the Y consistent with the positive and the negative. But okay, so we've got our graph here. Now, as far as like your domain and range related stuff for this, well, now we're just looking at the function holistically. So as far as domain goes, that's where my discussion regarding what do you do with these joining points starts to matter a lot. If you do have what we had here, which is non-inclusives overlapping with inclusives, you default to inclusive, which means when we look at our full domain left to right, there is no leftover white circle to worry about, and we can see these continue on forever. Like the outskirts of the graph are shooting off to infinity in the positive direction and infinity in the negative direction. So domain for this one is just going to be all real. If we did have things like this with an open circle here and an open circle here, then we now have to do stuff like exclude the 3 or whatever, as long as you have open circles only in that vertical slice, then you've got to make sure you're excluding them. If, for instance, you have an open circle up there, but a dark circle down here, that still counts as inclusive because in that vertical slice of x equals 3, there's at least one point that exists on the graph. So we don't cut that out anymore. I kind of gave those a bit rapid fire there. Did it make sense enough, the 3 little scenarios that we had there? Happy to explain them with more pictures if needed. A bit more? Yeah. So basically, you might come across scenarios like what we just had. So that was, we had this function and then it bridged off there, both inclusive. This is just now all real, right? Like we had in the, if I redraw this back to what it was, this is just all real because it's all connected, no white circles. The next kind of scenario that we run into is if we have an inclusive and an exclusive right above it. What do we do there? Well, again, domain is just looking horizontally, making sure that every single x value is accounted for with a corresponding y value. So all these are accounted for. The only bit that's a bit weird here is this, which is, okay, is that x equals 3 included? Well, it's included down here. So even though it's not included up there, there is still at least one spot on this graph where there is a inclusive dot on it. So this one also ends up being x is an element of all real because because x equals 3 does still have a value down here. The only way you do have to exclude something is if on that slice both are non-inclusive. If nowhere along this vertical slice of x equals 3 has a corresponding y value or has a dark circle, then you now have to exclude the 3. I think those are all the main things to watch out for there. Those are your 3 main scenarios. How's that? Any more clarification? Okay, lastly is range. The exact same rules apply for range, but we're now looking in the horizontal direction, horizontal slices. So basically, I'm looking at all my y values, and I'm saying, okay, do each of these little slices have at least some value that exists on that slice? This one, absolutely it does. Right, this shoots off to negative infinity, this shoots off to positive infinity, and everything is joined up. So as far as how you say range, you can get away saying like y is an element of real. You can say f of x is an element of real. It depends on what function you're given and like what it's labeled as. Even just saying range is all real numbers, like rain, real, that works fine. Now, if we go back to like these examples here, we're going to have a similar sort of thing. So let's have a look, let's have a think. Okay, I've got dark circle, open circle, like that, with 2 little branches off from it. So again, looking for possible y values, we're pretty much only ever concerned about where there's discontinuities, where there's these white circles here. Now I'm looking horizontally, I'm looking at all the y's. Is there a given y for that thing? In this case, there is. So although this one doesn't have a y, this one, for the same y value, does. So in other words, this would now have whatever that is. Let's call this -3. This would now have from -3 to infinity, because these shoot off to the positive infinity, and this little bit's accounted for there. When we write the symbol for real numbers, do we have to write it like it's in the textbook? You could probably get away with just R. Yeah. It's one of the least hardest ones to do, at least in my opinion. Like the Z is a bit of a pain in the ass to do. I've already screwed it up, hang on. Z for integers is kind of annoying. Real I don't find too bad. You just do 2 parallel lines and then finish your R. But yeah, just writing R, you'll get away with it. There's no worries. But okay, so that's that first little example there. Oh, sorry, the second one, I guess. Then last option is going to be quite similar, but this time they're both white circles there. So white circle, white circle. Let's pretend these are parallel to each other. In that slice, let's say it's y equals 3, there is no y value there, so you have to exclude it as part of your range, because they're both exclusive. So like, you could even go to the extreme of it, where you have a graph that is here and then there. Not only are you excluding these values, but also everything in between, because there's a big wide gap there. So in summary, you're pretty much only looking at where are there the open circles, and then making a judgment based on, is there an X or Y represented somewhere along that slice? If there is, include it. If there isn't, exclude it. How's that? Domain range of piecewise functions. Something you definitely have to practice, and you'll need it for more complicated functions that have like your asymptotes. This is where when you have like that natural log that we had actually in the practice SAC that I have, like the natural log of x squared plus 4, like you're not taught how to sketch the natural log of x squared plus 4. And even if you have the CAS on it, suddenly you can at least see what's going on. So it's not even necessarily that piecewise have this issue. It's more so just like strange functions have this issue. Let me change that ever so slightly so it does break. Yeah, like that. Like you get a graph like this and you're like, okay, well, what's range and domain of this? Well, range is probably the easier one to get because shoots off to negative infinity, shoots off to positive infinity. We can clearly see by the trend on this. And maybe we can even zoom out and in depending on how confident we are of the trend of the graph. But this is going to shoot to positive and negative infinity. As for what you now have to do for domain, well, we can see there's this big gap in here, right? Now, how big is that gap actually? This is where a graphical approach doesn't necessarily always work out too well, because this looks truncus-like, but it might not actually just be an asymptote of x equals 0 here. For instance, if I do zoom this all the way down to like negative 1000 and let it load. Oh wait, does it just flat out not exist down there? Well, I guess it wouldn't. Yeah, that's true. Let's find it again. Nope. Point being, it's... Oh wait, shit, so that means my range was off. Yeah, okay. This is why it definitely pays to to zoom out when you don't really fully get the graph. So negative. Yeah, okay, this thing just actually stops earlier, way earlier than I thought it would. Not bad. So yeah, giving the range would just be whatever the minimum of this is. Now, as for getting domain of that, a couple ways you could do it. You could use the graphing tools to figure out where these are, or you can just go back to fundamentals and say, okay, well, the natural log is only defined for positive brackets. So I need to, in other words, figure out where is x squared minus 4 positive. That's going to be from plus minus 2. So even though one of these kind of looks like it's below the other, I'm reasonably certain they do end up being the same thing, because where the logarithm breaks is the same. It should be symmetrical. Plus minus 2 are where you get natural log 0. Let's have a look. Does it do it? Find minimum. Yeah. It just doesn't even want to find it. Nice. Alright, so I guess you are kind of forced to use the other approach that we talked about. But we talked about this when we did our maximal domain and implied domain section here, which is just go back to the cheat sheet of where are these functions defined, and then, yeah, when you have a composite function, you're just combining the two together. You're looking at them each individually, and then going from there. This is a nice lesson, actually, which is typically best to do your domain first, and then once you know your domain, fit the range back in afterwards, because you sort of make the mistake of just assuming that it would shoot off forever. But in fact, on further inspection, we see that it actually cuts off earlier. So, something to watch out for. Is there anything else that I should clarify about this sort of like domain and range stuff? Feel free to stick around a bit. I'll be here for a couple of minutes more. And even if you have any other questions regarding anything else you're doing, I'll be here to answer them. Otherwise, I'll let you enjoy the rest of your night. Thanks, guys. No worries.
Okay, I've got a question. So, when do you usually post the class recordings?
Yeah, so what's happened, oddly enough, is I go to post the recordings and I got an error which said limit of 200 videos in a course. And so I was like,
Well,
oh, great. So I now have the fun job of separating all the 2025 recordings into their own little course module. Um, and you would think that you could delete folders at a time, but what happens when you delete a folder is it just deletes the folder itself and spits out all the videos. So I have
that
the
even
fun job
means.
of manually deleting as many videos as it takes to get some space back. They all exist on my YouTube channel, so you see that all those go to my channel directly, so you can watch them there. But I gotta now just sort of tidy that up a little bit.
All right.
Yeah, it's it'll be a
And
little bit of a pain, but it's fine. So it's
mm,
every week, end of week, that I post them.
that's it. All right.
Yeah, and if you need them earlier, let me know. Like I kind of just do it end of week just because it's my process. But if you have a video like, oh shit, I remember I need to like revise what was how to look there, let me know. More than happy to post it earlier when I can.
All right. Okay.
Easy.
Yeah. Thanks. Have a good
Yeah.
day.
You
Or
too.
have a good weekend.
You too.
Hi Chris, I was just wondering the cache shortcuts for derivative, piecewise, and limit.
Yep. I heard derivative and piecewise. What else did you want to see?
And limit.
And limits. Okay, derivative shift minus is the fastest way to
Shift
get there.
minus. Yeah.
Otherwise, you got menu 4.1, which is, I mean, if that's already built into your DNA, then that's
Yeah, and
also
I was running the shortcuts because I saw you using a couple. So
yeah. So yeah, shift minus and shift plus are for derivative and integral, respectively.
shift plus integral.
Yeah, shift plus gets you the integral.
Okay.
That's right. Limits, I just go into the menuing for it. I don't think there is a specific shortcut for that.
Cool.
Unless you meant when I just shoved in infinity, in which case that's just pi. The pi button has the infinity.
Okay. Okay.
So, if I do like h of pi button and then just toggle over to infinity, I'll get that.
Okay, yeah, I was a little bit confused when you did that. I was like, what?
Yeah, that's fair. That was limits, that was diff. What was the other one, sorry?
Limit. Oh no, wait.
Wait, the
Piecewise.
piecewise, right. Piecewise is the button next to the book. And specifically, it's going to be that one there because that lets you set the number of things you want.
Wait, is it the one on the left of the book? I can kind of
Left of the
see
book.
on your
Yeah.
Okay,
So
yeah.
left of the book there. It kind of looks like a piecewise button
Yeah.
itself.
What's the other stuff in there? I'm just trying to
this whole thing is just structures that are common. So you got your fraction structure, your exponential, the root, some logs. These, I don't really know what these are actually. They look kind of like half piecewises, but no domain. Got the absolute value, got the matrices, which you won't use. Some sum related stuff. You got diff as well as the nth derivative. So if you wanted to take, like, I don't know, the fifth derivative of a function, go ahead and do that.
You would normally use that for d over dx, so right? That one you just did.
Yeah, just defaulting to regular diff. You're never going to need to do like the fifth diff of anything. Maybe d squared, you might go straight to second diff, but that also, like, I won't do second diff on anything without literally defining each individual step along the way, because usually if you're doing second diff, you kind of want the first diff as well defined somewhere anyway.
Yeah. Are there any other good shortcuts?
Any other good shortcuts? I have a CAS document actually of the common things that I use.
Cool.
Yeah, if you have a look at the school miscellaneous resources, I've got a CAS guide in there. Let me just double check that's still there.
Yeah, that would be pretty helpful.
Yeah, it's got.
Oh, is it at the bottom? Miss resources.
Yeah, miss resources.
Yep, CAS usage.
There we go. Yeah, there should be a bunch of little stuff in there. It teaches you what all the buttons do, and also functions by topic. So, if you're like, I've got like a little section of global functions that you use everywhere, some calculus related stuff specifically, probability related stuff. What else is there? Yeah, pretty much everything in there is stuff that I use on a somewhat regular basis.
Yeah.
But yeah, have a browse through that.
Cool. I didn't have time to ask this today, but there was something I wanted to cover, but maybe we can do it, I guess, the next Friday. I was wondering if you could put it in to cover or review the area under a graph.
Review area under graph. Yeah, we can do that.
Yeah, I was going to ask today, but I think we just ran out of time.
Yeah, that's fair. Area under graph. I mean, let me just check the time real quick. Do you want to do like a full comprehensive review, or do you want me to just sort of give you like 2-3 minutes of having a look at it again?
I don't mind if you don't have a problem, then
yeah, I just wanted to like get an idea of how long we wanted to spend on it. I've got like a couple minutes, but if you wanted like a full class on it, that'll be a different story.
Yeah, I mean, yeah, just a review would be fine.
Yeah, just a brief review. Sure.
If you don't, sure.
Yeah, that's fine. So area under curve, basically what you're doing there is definite integral. Like that's your bread and butter, absolutely. As long as you have the function, area under a curve can be found via doing the definite integral over whatever domain you're trying to integrate over. Now, that's the bread and butter version of it, which is any definite integral will give you area, but more specifically, what it gives you is signed area. So if you don't do anything, whatever the location of your function is, depending on if it's above or below the x-axis, will give positive or negative area. So in other words, if you just integrated from 1 to 4 here, you would be adding the positive area and subtracting the negative area there. So whatever that is, minus whatever that is your answer.
Okay.
That's definite integrals. Now, they give you signed area. Typically, what you want is any of these. Unsigned, total, bound, anything like that. What you want is to make sure that all of this is considered positive. There's 2 main ways of doing it. Both of them rely on the fact you're splitting up your integral in 2 stages. So first you want to sketch your graph and identify where is their negative area, where is their positive area. Split up.
I just had a quick question. Do I need to know left and right endpoint rule or just trapezium?
Good question. It's in the textbook, but I noticed that every exam since introducing trapezium rule has just used trapezium rule.
Yeah, because left and right endpoint is just estimates. So
I mean, both of them are estimates, but the trapezium is a better estimate. And I think even in the textbook itself, it kind of just tells you it exists and then just doesn't actually get you to use it. Like I'm pretty sure all of these estimating the area, where is it? I'm fairly certain all the area estimation stuff used the trapezium rule anyway in the textbook as well, wherever that was. Okay. So
I think it was like 11A.
Yeah, okay. Let's do a quick look. So it teaches you about them, more so to introduce that, more so to introduce this topic.
Yeah, and I assume you have stuff on all this on the classroom, right?
Yeah, the
okay, cool.
estimating area stuff is in the integration section. That's all this stuff. Rectangle one, as well as the trapezoidal one.
Cool. I'll have a look at those tomorrow.
Sweet.
Awesome.
All good?
Yep. Thank you so much, Chris.
Easy. Yeah, no worries. I'll leave you to it.
Sounds good. I'll see you on Monday.
See you Monday.